I'm okay, done.
Yes. Today's speaker is Dr. Srikar Vijayasarthy, currently working as an assistant professor at the Department of Audiology, All India Institute of Speech Engineering, Mysore. He completed his undergraduation, post-graduation, and PhD in audiology from the same institution where he currently is working. He worked at various positions like research officer, clinical audiologist, and JRF previously. He has many national and international publications in the field of audiology. He has also received many awards like National Talent Search Examination State Level Scholar, the Alan Samuel SSV Award, Manohar Memorial Award. It's my great pleasure to invite Dr. Srikar Vijayasarthy for today's talk. So, please. Srikar, sir?
Yeah. Can you hear me?
Yes, sir. So, can you please share your slides?
Yes. Yes. Is the full screen visible?
Yes, sir.
Okay. Good morning, everyone. Thank you for the nice introduction, Sumanth. At the outset, I would like to thank JISHA for giving me the opportunity to share what I understand about statistics. You can see a small disclaimer there. I'm not a statistician, but an audiologist by qualification. So I'll share how and what I understand about analyzing data and interpreting data. And if you feel something is vague or is not clear, okay, please do let me know. I'm open to all kinds of suggestions and discussions. Um, Next, given the technical nature of the subject and those who will need it a lot more, I have opted to keep this at the beginner to intermediate level. So with maybe a bit of advanced concepts here and there. Please bear with me there. So let's start. The topic is decoding statistical findings, its interpretation, and writing style. So it basically boils down to how we analyze data, how we interpret data, and how we report the data in an accurate manner while avoiding the usual pitfalls and overgeneralizing our results. So let's start directly with our data sets. Okay, this way we'll understand the concepts so much more better. So we have a subject number, okay, 1 to 10, and the variable here is SNR50. So the second column is SNR15 young adults, and the last column is SNR15 older adults. So we are comparing SNR50 values between young and older adults in 10 subjects each. So how do we analyze this? Okay, what do we do next? First and foremost, okay, once we have tabulated it, we have to understand the nature of the variables. So what are the variables that are under consideration? So variables can be continuous or discrete or categorical, right? And or it can be independent and dependent. Independent variables are those that which are manipulating. So in this case, that would be group. And dependent variables are those that we are measuring. So in this case, that would be SNR50. And next is scale of measurement. What is the scale of our data? Is it nominal? Is it a mean? Is it ordinal? Does it have bands? Interval? Does it have meaningful equal intervals between them? And finally, ratio scale. Does it have a true zero? Okay. And all the other qualities that I mentioned before. So if we go back, we can see that the dependent variable, that's the SNR50, is a continuous variable. Okay, it can take any value, including 0. There is a categorical variable also, that would be the group. So that's not immediately obvious. okay, because we have not, put our data like that. And the subject's number here is purely nominal. Okay, we can basically ignore it. So once we have understood this, why this is so important is because the nature of the variable and the scale of measurement will affect uh, what tests we will use for analyzing the data. Okay, not only that, it also affects how you tabulate your data. Take a look at this. This is SPSS. The SPSS requires that you tabulate the data like this. So the categorical variable will be one variable, okay, which you have to mention in a single column, and the dependent variables have been all shifted into a single column like this, right? So if you have the same condition and many groups, they'll all go into a single column like this. Okay, so different groups, same conditions, single column. Okay, and different conditions, they will go into different columns. So this is why it's so crucial that we understand the variables that we are measuring. Okay. So we have tabulated the data, understood the variables, and reorganized our data tabulation. What next? Next would be you need to understand your variable trends. Okay, so what is the trends in your data? So take a look at this. This is referred to as exploratory data analysis. Okay, so we plot different kinds of graphs and we try to understand the distribution of the data. We try to identify outliers. Okay, I try to understand the trends that are present in the data, and finally, we also try to visualize if there is a normal distribution or not. Okay, only after this do we really understand our data, and then we can do meaningful inferential statistics. So, top left, you can see the histogram. Okay. So just by looking at this, okay, you know that young versus old, there is a separation. There are two very distinct distributions, right? With a small amount of overlap in the middle. Okay, you already know that the two are quite different. Not just that. Look at the shape of the data. So it's nearly normal in both cases. So there's a peak in the middle, okay, with the extremes being smaller. Next, top right, look at the box plot. Okay, and immediately you'll notice that the middle line is basically the median. So immediately you know that older individuals have poorer SNR50. Okay, so poorer in the sense that it's nearer to zero, whereas younger, okay, it's away from zero. Okay, negatively. So they have better SNR50. And please note that in the younger adults, okay, you will see two dots. Those dots represent the outliers. This is why exploratory data analysis is so useful. It will help you identify whether there are outliers in your data. And then you'll need to determine what to do with this. Okay, what to do with this outlier. Outlier transformation, outlier analysis is basically a separate discussion in itself. But boil down into something simple, we'll need to identify whether these outliers are genuine or not. Okay. So, is it by errors, okay, on the part of the subject, or due to measurement, okay, or during data entry something went wrong, okay, or is it that the subject genuinely performed poorer? Okay, if it's the latter case, that is the subject actually performed genuinely poorer. Okay, I would prefer that I'll keep the outliers. That's what we'll do here also. Okay, these outliers, you'll notice that there is one outlier which is somewhere around -8 or so. Okay, that means this person performed really well. He has very good speech perception in mind. And then there is one value somewhere around -3 or so, okay, which is similar to that of older adults. So this person genuinely performed poorly. So these both are genuine outliers. So we'll keep it. Okay. And next, you will see the scatter plot. So in this case, scatter plot is actually not very necessary. But again, I plotted this just for us to visualize how different each individual data point is. Okay, scatter plot will tell us the individual data points. So we can see that older adults have higher scores, okay, have a lot more variability. Okay, that's obvious from this graph, right? Whereas the younger adults, they are largely clustered around a similar value. Finally, let's look at the QQ plot. QQ plot will tell us whether there is a normal distribution or not. So there is a middle straight line. If the data points lie largely along that straight line, it means that the data is normally distributed. So just by doing an exploratory data analysis, we understand that the data is largely normally distributed, that older adults have poorer scores and have a lot more variability. Right? So this amount of data is already available with us without doing any inferential statistics. The idea is to see whatever trends that we are seeing here, are they actually statistically significant? That is, whatever we are seeing in this sample, can we generalize it to the population or not? For that, we need evidence. So the trends in the data and the data distribution, okay, the way to understand the data is through exploratory data analysis. So what we have visualized as figures, let's visualize as numerics. So you can see the mean, median, standard deviation, okay, as well as the range, minimum to maximum. So again, you can see that mean is -3 for older adults, for younger adults it's -6. Okay, what we visualize. And please see this, mean and median are almost similar. This is a very good indication that the distribution is normal. Okay, and look at the standard deviation here. It's 1, okay, in older adults, 0.7 in younger adults. Again, there is a lot more variance in older adults. And look at the range here, -5 to -1.75 in older adults. Younger adults, -7.25 to -4.75. Okay, so the key here is that even the worst performing younger adults, okay, is performing similar to that of a best performing older adults. So that's the small amount of overlap that we discussed. Next, so let's confirm normal distribution. So we have done Shapiro test of normality and look at the p-values here. It's 0.7 and 0.8, okay, for older and younger adults. As long as they are greater than 0.05, okay, we can say that the data is normally distributed. So what next? So let's do the inference. Let's see whether the trends that we are seeing are they statistically significant or not. By that we mean whatever trends that we are seeing in our sample, can we generalize it to the population? So we can do parametric tests or we can do non-parametric tests. So parametric tests make assumptions. This is very, very important. Most of the times we see in articles, okay, that they don't specify whether the assumptions were met or not. Right? So parametric tests make assumptions, and if those assumptions are satisfied by our data, they have greater power. Okay. Power means if there is a difference between these two groups, can our test identify it or not? So that's power. Okay. So if H naught or the null hypothesis is not true, can our test reject it correctly? So that's power. So parametric tests are always preferable. Okay, but given that assumptions are satisfied. So what those assumptions are, we'll take a look. But before that, if those assumptions are not met, you can do non-parametric statistics, which make no assumptions. So it's our go-to procedure if the assumptions are not met, but they will have lesser power. Okay, so there's always a trade-off in statistics. You will see that again in the game. Okay, there's a trade-off happening. Okay, because they don't make assumptions, what they do is they'll convert all our data points into ordinal scale. They convert everything into ranks, okay, and see if there is a significant difference. So thereby we'll lose a lot of power. So what are the key assumptions, okay, of parametric statistics? First one is normality. Do we have a normal distribution or not? Okay, in our case, that has been met. So there is a subtle point here. If a distribution, if the sample size that we have is small, then this is very important that our data is normally distributed. Okay. If our sample size is larger, okay, so we don't have a very strong definition of what is large. Okay, it actually depends on the variance. But let's say it's greater than 30 or so, then even if the distribution is mildly deviates, okay, from the normal distribution, we can still do parametric tests. Why that is okay, it's going into a bit of depth. There's something called central limit theorem, okay, which states that as long as the mean, okay, of the sampling distributions is normal, okay, then even if the sample distribution itself is not normal, okay, you can go ahead and do parametric statistics. Okay, so making it very simple, large distributions, large samples, even if normal distribution is not there, if there's a slight skew, parametric tests are quite robust to that deviation. But small sample size like ours, okay, we will need to have normal distribution. Equal variance means we have two groups, right? They should have similar variance. Okay, there should not be a lot of difference, okay, between these two variables. That criteria is also met here. Okay, 0.7 and 1 also, right? So, but there's a test also for that. So it's called Levin's test of homogeneity of variance. Okay, in our case, again, you see that the p-value is greater than 0.5. That is to say, statistically speaking, the variances are equivalent. Independence means the way we collect data, okay, has to be random and independent in each population. Okay, it should not have a particular bias. So it's true for all statistical tests. Okay, independence is the bedrock of all statistical procedures. Level of measurement, this is important. All parametric tests require that the scale of measurements, okay, is at interval level or beyond, okay, or ratio scale basically. You cannot use ordinal scale or nominal scale, okay, and do parametric analysis. And of course, there should not be any extreme outliers. So all these assumptions have to be met before you do a parametric inferential statistics. So that's why we have checked for normality using Sapir-Whorf. We have checked for equal variance or homogeneity of variance using Levin's test. Okay, independence is assumed, that's a part of your methodology. Level of measurement is a ratio scale and hence it's a fix. So this, we have done an independent test. So we have two independent groups, okay, and we have compared the SNR50 between the two. So this is called independent t-test or unpaired t-test. So the first column is Levin's test of variance. We'll leave that. So please look at this. This is what is important. There is a t-value, there is a degrees of freedom value, and there is a p-value. So we need to understand what these mean to actually interpret it correctly. Okay. So let's take a look at this. Okay. T is basically a test statistic. Okay. What that means is basically, let's go to Z distribution, okay, or the Z distribution. Okay. So what it is that when we subtract, okay, the means between the two groups, the null hypothesis states that there is no difference, right? So that's why in the middle there is 0. Okay. And look at this here, okay, the Z value. It's mean of one group minus mean of the other group divided by the standard deviation. Okay, so that's actually pooled standard deviation. That is because we have two groups, we'll pool the standard deviation, but that basically represents the combined standard deviation. So the Z value or the Z value is the difference between the two groups divided by the standard deviation. Okay, so that's very simple. That's how you get the x-axis here. So when there is no difference, it's 0. Okay. When there is x1 is slightly greater, you'll have positive values. Okay. When x2 is slightly greater, you'll have negative values. Okay. So this is the Z or the Z distribution, which is the basis for all other distributions that we'll see later. Okay. So the Z distribution, okay, on the x-axis has 0 in the middle and different standard deviations on the right and the, let's say, +1, -1, +2, -2, like this. Okay, so that's the red line that you are seeing. Okay, that's the Z distribution. It has most of the values that are coming in between, and it will taper towards the ends. Okay. Next, please look at the red dotted line. Okay, that's called the Z critical value. So there are two lines on either side, right? Okay, one on the right, one on the left. That represents the 95% confidence interval. Okay, that means to say 95% of the times the data will fall within this area. Okay, if it falls outside of this, okay, there is 2.5% on right side and 2.5% on the left side. So totally 5%. Right? So if a value falls outside of this critical line, okay, we will say that there's a good chance that that value doesn't fall within the null hypothesis. Okay, so this is the basis of our p-value. So what do we have? We have a z distribution, and we have two lines on either side. Okay, that we refer to as critical value. Okay, so that critical value represents, okay, 95% of the possible values, okay, that are present. Okay, if the values are falling outside of that, okay, then we say that the probability is lesser that it belongs to the null distribution, and hence reject the null hypothesis. If it falls within the critical value, then we say that there's a good possibility that it belongs to the null distribution, and hence we retain the null hypothesis. Okay. So T distribution that we have, okay, is similar to Z distribution. Again, a difference between the mean, okay, and a standard deviation. Okay. But please identify the differences between them. Okay, the blue line is the T distribution. T distribution is shorter in height, okay, and look at the extreme ends. Okay, it's broader at the extremes. So T distribution is basically Z distribution, which is shorter in the middle and broader at the base. Okay, so it represents a data set where there is a lot more variance. Okay, so whenever you have a small sample size, where your variance will also be larger, and for that you use a T distribution instead of a Z or a Z distribution. When you have a large sample size, we use a Z distribution. When we have a smaller sample size, we use a T distribution. And correspondingly, look at the blue dotted line here. It's located away, okay, from the Z line, right? It means to say that you need a stronger evidence, okay, to say that a particular value belongs to the null distribution or not, okay, when compared to the Z distribution. Okay. So again, simplifying everything, Z basically represents the difference between two means, okay, divided by the standard deviation. T is also the same, just that it will account for larger variance in the data, and hence is more useful for smaller sample sizes. Okay, so here we have our T distribution. Okay, okay, in between you see our T distribution and our test statistic. Okay, how did we arrive at our test statistic? We subtracted the two means, we divided by our standard deviation plus some accounting for variance. So that's what test statistic means. Okay, so based on our data, we derive a test statistic that will compare with the distribution. Okay, so that's the process. Okay. Based on the data, we derive a test statistic that will compare with the distribution that we want. So here, because we are running the t-test, we have a t-test statistic, and that value was 7.5. Okay, so this is our null hypothesis. So this is our test statistic. So what is your intuitive interpretation? This test statistic is lying well away from the null distribution, right? So how do we interpret this? Given that the null hypothesis is true, okay, the probability of this value occurring is small, very, very small. And to be more accurate, it is 0.03%, right? So this is the framing of the interpretation. Given that the null hypothesis is true, what is the probability that this kind of data can occur? Okay, and in our case, it's 0.03%, very, very less, right? So what do? We reject the null hypothesis. We accept the alternative hypothesis. We reject the null hypothesis that there is no difference between the two groups, and we accept the alternative hypothesis that there is a significant difference between the groups. Okay, it's quite simple, right? So, and look at the values here. P is 7.5, that's our test statistic, and DF is the degrees of freedom. Okay, degrees of freedom basically represents the uh, amount of unique values that your data can have. Okay, to give you a simple example, let's say we have 5 people whose height we have measured. Okay, so 5 people's heights we have measured and the average we have, right? So subject 1, subject 2, subject 3, subject 4 heights we have plus average. So with this, we can measure the height of the fifth person, right? So we need not actually have that particular fifth person values, person's height. Okay, with just these 4 values plus the average, we can calculate the fifth person's average. Okay, so that is to say, with just 4 values of data, okay, we can arrive at all the information that are necessary. So what are the number of independent values possible here? Subject 1, 2, 3, and 4. 4 will be the degrees of freedom. So degrees of freedom represents the number of unique values possible. Okay, in our case, we have 10 plus 10 subjects, right? So that's 20. And we have 2 groups. So that's 20 minus 2 degrees of freedom. Okay, I hope it's clear. We have discussed what is a test statistic, how it derives, what is degrees of freedom. Okay, so it represents the number of independent values possible, okay, within our data. So why is it important? More the degrees of freedom, okay, your T distribution will tend towards Z distribution. Okay, so your data will become more and more easy to interpret. Okay, so that is why distribution DF is also very important. That needs to be mentioned. Okay, so if so that's the p value. So what is the p value? Okay, p value is given that the null hypothesis is true. What is the probability that this particular test statistic is appearing? Okay, is the probability more? Is the probability less? Based on that, you interpret. So if the probability is less, okay, then you reject the null, accept the alternates. Okay, what about this? Okay, so still greater than the critical value, so we reject the null, accept the alternates. Still greater than the critical value, okay, reject the null, accept the alternates. Okay, here, okay, now it has crossed the critical value, right? So look at the p value now. Okay, it's 0.09. Okay, it's greater than 0.05, right? So it means to say there is a 9% chance that, okay, this particular test statistic belongs in the null distribution. Okay, so how do you interpret this? Okay, very important. Okay, we interpret this as we retain the null hypothesis. Okay, we don't actually accept the null. Okay. So I hope you understand why. P value by definition says given that the hypothesis is true, null hypothesis is true, we have already accepted the null. Okay, and we are testing against that. Okay, so if there is not enough evidence, okay, to reject the null, how do we frame our interpretation? We retain the null. Okay, we have already accepted it, right? So we should actually never say that we accept the null hypothesis. That's wrong. Okay, logically speaking, that's wrong. Okay, people do write it, but it's logically speaking wrong. Okay, so we retain the null hypothesis, or you can say that there is not enough evidence to reject null hypothesis. Both are right. Okay? So look at this. This is what I was talking about. Why degrees of freedom is so important. So as the degrees of freedom increases, okay, it will tend towards a normal distribution. If the degrees of freedom are less, you will see a very short height and very broad base. Okay, and it will tend towards a normal distribution as the degrees of freedom increases. Okay. So we fixed that value, right? 0.05. If the test statistic is the probability of that test statistic occurring, that's the p value, is more than 5%. 0.05 is 5%. So it's more than 5%. we accept, sorry, we accept the, we retain the null hypothesis, okay, and reject the alternate hypothesis. So, who framed this? Okay, who gave this or who fixed it at 5%? Okay, that's very, very important. How do we decide our alpha? So, this is called alpha value, or we also refer it to as the false positive error. So, what's false positive? It means that if the null hypothesis is true, what is the chance that we reject it? So please take a look at this. Let's say this is our distribution, okay? And if the data point occurs somewhere here, okay? So after in the red region, we reject it, okay? So that's our understanding, right? So if the value is greater than 0.05, we reject it, but it's still the part of the same distribution, okay? So even though null hypothesis is true, we are rejecting the null hypothesis. So this is called false positive, okay? And we fix it at 5%. So it's kind of funny, why 5%? Because we still don't know. Okay, there is no agreement why 5% is empirically useful. Okay, but because it has been done for a long time, we are still doing that. Okay, so a key point that I want to stress here is that you can change that. Okay, so if you say that you want more accuracy, you don't want false positives at all. So it depends on the context, right? So physicists, for example, do very, very accurate pinpoint measurements. They require a lot more accuracy. Okay, and they usually fix alpha at 1%, 0.01. So say it's not fixed at 0.05. Let's say you're doing a exploratory data analysis. Okay, so the study is exploratory in nature. Okay, you don't know, you don't have a very strong hypothesis. Okay, in that case, okay, you are looking for variables that may be important. Out of so many variables, what are the important variables that I should study? Okay, so you want to do a large scale study, but before that, you want to do a small study, small exploratory study to identify variables that are important. Okay, in this case, okay, what you want is not accuracy. What you want is more power. Right? In that case, it is fine, okay, to have to set the alpha at, let's say, 10%. Okay? All you need to do is to justify, okay, your alpha. Okay, why are you using 5%? You should be able to justify. Why are you using 10%? Again, you should be able to justify. Why are you using 1%? You should be able to justify. Okay, this is a very, very important, because we by default we keep 5%, right? There is no strong empirical reason to it. Okay, you should be able to justify why you are using what. So here, okay, so I use another term, right? Power. Okay, so let's visualize that here. So what we see here is in the middle, you can see the null distribution. Okay, and you can see the red shaded area. Okay, by now you understand, right? What does it mean? Okay, it means the false positive region. Okay, even though the null is true. Okay, should the p value fall here, okay, we reject it. Okay, we reject the null. Okay, so that's the false positive region. Okay, let's say our distribution here, the data that we have, doesn't fall in the null. It's very, very obvious now, right? Okay, it doesn't fall. There is a large difference between the two groups. So our distribution is actually the second one, what you see on the right. Okay, so this is our second distribution. Okay, you can see an overlap between the two, right? Okay. So look at the critical value. Okay, there's a strong line there between between. So if the test statistic falls to the right of it, okay, we reject the null, okay, and accept the alternative, and you'll be right. Okay, but if the test statistic is falling to the left of the line, okay, so remember, we know that there is a difference between the two groups. The two distributions are different, correct? But even if that's the case, should the test statistic fall to the left of the line, we still reject it. Okay? So what is this error referred to as? This is the type 2 error. So the type 1 error is false positive, okay, and type 2 error is false negative. Okay, so that's the blue shaded region where even if the null hypothesis is not correct, you still accept it. Okay, why do you accept it? Because the p-value is greater than the alpha that you have set. That is, usually it's the 5%. Okay. So what I'm trying to discuss here then, based on the alpha that you set, your beta will also get affected. Okay, that is, if you want more accuracy, okay, that is, you don't want false positive errors. If you increase this, okay, so what will happen? Okay, intuition should say that there will be a exchange, right? There will be a trade-off. If the red shaded region increases, blue will become smaller. If the red shaded region decreases, blue will become larger. Okay, so more the amount of blue, lesser the power. Okay, so take a look at this. Okay, so let me shift the alpha to left. So what is happening to the blue shaded region? It's lesser, correct? This, okay, the blue shaded region is decreasing and decreasing, right? Take a look to the left. Okay, this means to say, if I change my alpha, okay, the beta will also get affected. There's a trade. So if you increase alpha, the beta will be smaller. Okay, that is type 1 error rate. Okay, if it increases, type 2 error rate decreases. Okay, this is a key understanding. There is a trade-off. So this ties in well with what I was telling you, that 5% error rate, alpha error rate that you fix will affect your beta, right? So if you want to have more power, okay, you want to identify differences that are present, okay, even if there is a false positive error rate increase. Okay, let's take an example. Let's say I want to know what are the important variables in which those with ANSP differ from normal hearing. Okay, those with audition disability, how do they differ from normal hearing? I want to identify all the important variables possible. Okay, so that I can do a detailed study, even at the cost of a few false positives. That is to say, even if certain variables are not significant, you will get it as significant. That's fine. Okay, but my objective here was not to be very accurate, but to identify variables which might be of significance for me to do a more detailed study. In that case, I will set the alpha as 10%. Okay, this is how to justify your alpha. Okay, so justify your alpha. Okay, and you can go take a look at this. Okay, have increased the alpha here. Okay, I set it as 10% and look at the power. The power increases. Okay, so it will increase to 90, 95% like this. So there is a trade-off between alpha and beta. So don't just be fixated at 5%. Okay, you can use 5% if you can justify it. Okay, alpha is false positive, beta is false negative. Okay. So what is more important or less important to you depends on you, the investigators. Okay, so depending on your objective, okay, you decide your alpha. Do you want it to be 1%, 5%, 10%? Justify it and go. So here it is. For our data, on the x-axis you see alpha, on the y-axis you see power, and you'll see that as I increase alpha, okay, that is from 3% to 5% to 10%, power increases. Okay, so this is what I was talking about. If you want to have more power, if your objective is to identify differences wherever they are present, okay, even though there might be a few false positives, go ahead and use a larger alpha. Okay, don't be fixated at 5%. But if the opposite is true, okay, that is to say you want accuracy, whatever differences you find, you want that to be accurate. Okay, even the cost of missing a few things that are significant, then you use 1%. Okay, so I hope I have conveyed the flexibility of the alpha value that you can set. Right. So how do we correctly interpret our p-value? Okay. So the p-value is very, very small in our case, right? 0.03. We say reject null distribution. Okay, and we accept the alternative hypothesis. Okay. This is what we write, okay, in our papers. Okay, but what our actual understanding needs to be is that basically there is a non-zero effect. means the two groups are not equal. And in the long run, you'll be wrong around 5% of the time. Okay. This is a key understanding. Remember, we said the alpha error rate as 5% means this particular conclusion of yours, okay, it will be true around 95% of the time. Okay, but 5% of the time, whenever you do the study, there's a chance, okay, that the test statistics will fall within the null distribution. So this is what we refer to as frequentist statistics. All right, that is, we use the term here. Look at this. In the long run, that is, if we repeat the study again and again and again, okay, most of the time, this is the conclusion you will come to. Okay, but 5% of the times, you might not come to that conclusion. Okay, so that's the false positive hypothesis. Okay, so p-value, intuitively, we understand it as, for this data, what is the probability of null hypothesis, right? Okay, for the data that we have, what is the probability that null hypothesis is true? That is how we intuitively understand. Okay, but that's not what p-value is. P-value is the inverse. What is it? Given that the null hypothesis is true, what is the probability of this particular data appearing? Okay, so the difference is not actually trivial. They are not the same. Okay, given that the null hypothesis is true, what is the probability of this kind of data is what is p-value, whereas what we want, okay, is given this data, what is the probability of null hypothesis, right? Okay, this is very, very important. So what I want to convey is interpret p-value a bit more cautiously. It's not immediately what to think, right? So be tentative in your judgments, okay? And this, whatever result we get has to be clarified by replications, okay? So I use the term frequentist statistics, okay? It means that that particular p-value statistics, okay, gains strengths not by a single study, but by replications, okay? So we have discussed again and again that there is a error rate, okay, 5%, 20%, like this, okay? So how do we make sure that what we have is correct? Okay, it's done by doing replications, okay? So what if your p-value is not significant? How will you interpret it? We retain the null, okay? We already have accepted the null, right? So what you say? We retain the null, or you say this is actually more justifiable. There is not enough evidence to reject the null hypothesis. This is how we need to interpret it. Okay. We don't accept the null because we already accepted it. That's the p-value by definition. We have accepted the null. Okay, and we are testing the data against it. We retain the null hypothesis, or we say that there is not enough evidence to reject the null hypothesis. It's like a person being convicted in the court. Okay, so in the court of law, but the person starts out as innocent, right? That is, we have accepted his innocence. Then we see the evidence. Does it support that or not? Okay, so if evidence supports that, okay, then we reject the null. Okay, and the person is given punishments. Okay, but if the evidence doesn't support it, okay, so we say that there is not enough evidence to convict the person. Okay, the courts actually don't say the person is innocent. Never. Okay, so the court will just say there is not enough evidence to punish this person. Like that, it's not. We don't accept it's not. We just say not enough evidence to reject it. Okay. So again, okay, in the long run, okay, you might be wrong. How many times? So if the p-value is significant, we say that in the long run, we might be wrong around alpha percentage of the times, right? That is 5% of the times, most of the times. Okay. But if the p-value is not significant, okay, then in the long run, you'll be wrong by around, yes, it's the beta percentage of the times. Okay, so when the p-value is significant, okay, there's a chance that you'll be wrong around 5% of the times. And if the p-value is not significant, you say that there's no difference between these two conditions, okay, you will be wrong around beta percentage of the times. Beta, okay, is basically 1 minus power. Most of our studies, we design it for 80% power. Okay, that is to say, even if there is a difference present, you might still find no significant difference around 20% of the times. That's a large number, right? So most of the times, if our studies are well designed, we will get a non-significant difference because the effect sizes that we deal with are quite small. Okay. What does it mean? Does it mean that there is no significant effect, that there is no difference? No, it's not. What it means is that, okay, your study, okay, might be wrong around 20% of the. So that's what it is. So that's how we need to interpret a non-significant p-value. Okay, so let me summarize. Okay, whatever I have discussed. What are the ways we can misinterpret p-values? We can misinterpret it as it's a false positive rate. It's not. Okay, it's not a measure of false positive error rate. That's your alpha, right? So we can say that null hypothesis score is P is non-significant. Okay, this is how we report it actually. This is how we write it. Okay, but at least in the background, we need to understand that we can go wrong. Okay, so p-value, okay, is not about the hypothesis, but it's about the data. Remember, what is p-value? Given this hypothesis, what is the probability of the data? So p-value tells you about the data. So how can you interpret this? You can say the data supports this hypothesis, or the data doesn't support this hypothesis. Okay, there is a subtle difference. You cannot say hypothesis is wrong or right. Okay, but this is how we write it. Okay, for practical reasons, to avoid long sentences, this is how we write it. Okay, hypothesis is accepted, rejected, but at least in the background, you need to understand that it's actually not a very right interpretation. Okay, so you have to understand that the p-value is about data, not about the hypothesis. And replication. Okay, because you have set the alpha value at 5%. Okay, false positive error rate at 5%. We cannot say that 95% of the time it will replicate. It will not. Okay, if you do so many studies of the same thing, 95% of the times, yes, you'll get a value within that range. But any particular application, will it replicate your study or not? Nobody knows. Okay, so because whatever we do, they are all in the probability domain. Okay, it may happen or it may not happen, but there are trends. Okay, so if somebody replicates your study and doesn't replicate, does it mean that your study was wrong? It's not. Okay, it's possible that the other person might be wrong. So what do we do? How do we know which person is right? There has to be another replication. Okay, and then we see the data is falling more towards whose study, like that. So this is how we update, okay, our feelings about what hypothesis is correct or not. Okay, so you cannot actually never prove the hypothesis, or you cannot actually disprove a hypothesis, because p-value is about probability of data and not the hypothesis. Okay, this is one point I want to stress. The p-value that you get is very, very strongly dependent on the number of samples that you take. Okay, so please take a look. Sample size on the x-axis, p-value on the y-axis. Okay, as the number of samples increases, p-value will drop. Okay, so just because you have a small p-value, okay, doesn't mean automatically that you have achieved something significant. It's not. Okay, you have to see whether whatever is of significance, okay, statistical significance, is of clinical significance also or not. Okay, let's take an example. Let's say you do a study between normals and cochlear hearing loss, and let's say you took 100 subjects in both groups. So quite a large N, right? So, okay, let's say the p-value is 0.03. Is it significant? Yes, it is. Okay, look at the effect size. Okay, so the difference between the two groups is 2%. Okay, so in one case, SI score was 70%. In the other case, it was 72%. Okay. So is it clinically significant? It's not. Okay, the patients themselves don't feel any difference. Okay, but you are getting it as statistically significant. Why? Because of your large number. Okay, so one of the most misunderstood part of p-value is that just because it is significant, okay, the results are significant by themselves. They are not. Okay, all it means is that statistically they are significant. It's up to you to determine whether that difference is large enough for you. Is it clinically significant? Okay. So beware of this. Okay. Whenever studies have large sample sizes, don't just look at the p-values. You have to look at something others also. What are they? Okay, we'll come to this. Okay, and I have to make a point about this also. Remember, p-values can be manipulated. Okay, that is, if you go on collecting the data and yet after collecting every, let's say, 10 data points, okay, you check p-value. If it is significant, okay, you stop there. If it's not, you collect more data. Okay, so you keep doing this. Okay, so you will achieve the p-value you want. Okay, and you will stop the data collection. Yes. Okay, so this is how p-values can be manipulated. Okay, or let's say you measure 20 variables. Okay, out of those, some three variables are just out of chance. Remember the 5% error rate? Just out of chance, they are positive, okay, significance. They are not actually, but because of chance, okay, they became significant. You report those significant variables. Okay, you don't even mention that you measure 20. Out of that, you are reporting 3 or 4. Okay, this is very, very important. This is called cherry picking. Okay, that is, you report only the data points that you want. Okay, and you do multiple tests, you report only those that are significant. Okay? So they are not wrong by themselves. All these things are not wrong by themselves. Okay, just that if we do it, okay, we must report it. That's all. Okay, so this way, readers will have an idea of how much weight, okay, these results need to be given. Okay? So these have an effect of increasing your alpha. You might say 5%, but if you do multiple measurements, okay, if you report only a few variables, okay, if you go on collecting till it's significant and then report, you increase that 5% to 30, 35, 40%. Okay, that is to say, then there is actually no difference in the population. In your sample, there will turn out to be a difference. So that's false positive. So be careful about that. Okay, so what is it I was telling you? P-values have all these problems. Don't just look at the p-values. They have their use. But along with that, you also need to look at the effect size. What is the effect size? In our case, it's the difference between the mean divided by the standard deviation. That's the cohency. What else was similar to this? Yes, it was V. Remember? Okay, V is also something like D in this case. Okay, so in our case, the D value was 3.26. Okay, that's a large effect size. Okay, so according to Cohen, 0.2 is small, 0.4 to 5 is medium, and 0.8 is large. Our C is 3.26. Okay, that's a very large effect size. Okay, means there is more than a 3 standard deviation difference between younger versus older adults, a large effect. Okay, so what's the use of this effect size? Even if the p-value is small, that is, it is significant. Okay, if the effect size is small, okay, the 2% SS score difference I discussed between normal versus cochlear loss, in that case, the p-value will be significant. Let's say 0.03 is significant, but the effect size can be something like 0.1. Okay, so how do you report this? Okay, we will say that there is a statistical significant difference, but it's a small effect size, nothing that you have to pay too much attention to. Okay, so combining D and P value in interpretation will make your interpretation a lot more rich. Okay, the opposite is also true. Okay, so if you find a large effect size, okay, let's say D is equal to 1.2, it's a large effect size. Okay, but your p-value is borderline. Okay, let's say 0.05 or let's say even 0.06. It is not significant, right? Okay, so you will report non-significant results, but no need to get disheartened. Okay, all it means is that the effect size is large at least in a few people, right? So that's why the average is large. So how you report this is that the effect size was large in a few people, while it was lesser in a few others. Okay, more studies would be required to get an accurate estimate of effect size. Okay, so this is the crucial understanding. Not everything is based on P. You also need to look at the effect size. Okay, that's actually more important than P. Okay, so look at this. The same effect size I have drew a confidence interval. Okay, what is the interval of your effect size? So look at this. Okay, in between there is -3 here, but the effect size is fetching anywhere between -1.8 to let's say -4.8. Okay. The key point here is it's not touching 0. Okay, it means to say that okay, just by looking at this, you know p-value will be significant. So with your 95% confidence level, you can confidently say that the actual population difference between these two groups will lie within this confidence interval 95% of the times. I'll keep inserting this. Okay, please understand that we are dealing with probabilities. Okay, you might be wrong. Okay, so wrong by 5% at best. Okay, at best you'll be wrong 5% of the time, but because we have so many other ways we can go wrong, right? Okay, our sample size might be low. Okay, the experimenters can get biased. Okay, we can make multiple measurements. We can measure multiple variables and report a few. Because of all this, the false positive error rate is never 5%. Okay, it will go up to 40%, 45% like this. Okay, so it's because of this that you report a particular finding, then you replicate or somebody replicates this, it's basically not replicating, right? So it's because of a large false positive error rates. Okay, so very, very important that we observe the effect size and we look at the width of the confidence interval. In our case, it's actually quite large. Okay, by standards of SNR 50, it's quite large. Why? Why is it large? It's because of a small sample size. Okay, so whenever the sample size is small, by default, the width will be higher, okay, larger. Okay, telling you that you are not very precise in your measurement. Okay, but either way, I know that there is a large effect size. Okay, but to get a precise effect size, I need to do a larger study. So a large effect size by default means that it warrants a larger study. Okay, to get a more precise. Okay, so this is the pipeline. Okay, of how we start from the data, tabulate our data, understand the variables. Okay, retabulate in accordance to that. Okay, do an exploratory data analysis. Okay, identify the trends in the data, understand the distributions in your data, identify whether it's normally distributed or not, identify outliers. Okay, and after that, you decide what is the inferential statistic that you are doing. Pick the right one, okay, based on your type of variable, and then interpret the value cautiously. Okay, and we don't stop there. We measure two more things. We look at the effect size, we look at the confidence interval, and then interpret it in a more holistic manner. So this is the report. Okay, this is a very brief report. Okay, so what I want you all to please observe is please take a look at the fifth line also. Okay, we have mentioned the mean and standard deviations. Okay, that's the descriptive part. And we have mentioned our inferential statistics. Okay, so what the statistic have we measured? It's T. Okay, and what's the degrees of freedom that we had in bracket 18? And what was the T statistic? Okay, and next we mentioned the P values, very, very low, right? 0.001. And we mentioned B value, that's our effect size. And we mentioned the confidence interval of our B value. Okay, so this is a comprehensive understanding or interpretation of our data. Okay, and you mentioned that the effect size is large, but it has relatively wide confidence. Okay, so this will tell the reader how to interpret your data. So what do they suggest? Okay, they suggest that there is a significant difference because the effect size is large. Okay, but you note that it's important to note that our variance leads to a wide confidence interval. Okay, so a larger study. Okay, that's your justification for larger study. Okay, might be more precise estimate of your effect size. So it supports, okay, validates, justifies the need for a larger study, which will give you a more precise estimate of what is the difference between the two groups, so that you can tailor assessment and management strategies to meet that objective. Okay, so that's it. This is the pipeline. Okay, there was a lot more to discuss, just that we don't have time. Okay, so this is a table of what tests to use for what kind of variables, okay, parametric, not parametric, etc. So thank you for your patient listening. Okay, I hope it was useful in some sort of the way for everyone, and open to taking questions. Thank you.
Thank you so much, sir. If any of the audience are having any queries, they can put up their queries on the chat box. It will be read louder. And we have given the feedback link in the chat box. I request all the participants to fill the feedback form kindly. If we don't have any queries, we'll further proceed with the presentation. I would like to thank Dr. Srikar sir for being as a resource person for today's webinar, for giving his valuable input on the statistical interpretation and its style of writing. Thank you so much, sir. I thank Isha and the Executive Council members and the supporting staff for making this event a grand success. And I also thank Dr. Pinki Singh, the Chief Editor of the JISHA Journal, for providing the platform for everyone to attend this webinar. I thank you all the participants for being here. Thank you once again. Have a nice day.
Thank you, Dr. Srikar, for your kind presentation. It was so informative for all. I guess all the audience has got the valuable information from your presentation. Thank you very much.
Yeah, thank you, ma'am. Okay, I had a lot of fun doing this.
Yes. Yes, thank you. We can conclude this, we can wind up this, huh? Sumanth?
Yes, ma'am. Yes, ma'am.
Yeah.
Yeah, thank you, everyone.
Thank you so much, sir.